Hey everyone, welcome to our next section on acids and bases. We're going to just start kind of right at the beginning. There's not a lot of calculations in this particular section, but as we move forward it would be helpful for you to have a scientific calculator that specifically has the log function in it. So let's kind of get started off. A lot of this stuff you can read through on your own. I'm just going to kind of go through the slides individually and just kind of try to explain a little bit of things as we start to go through these different types of acids and bases and their theories from three different people. So, some properties to start off with. Acids have several distinct properties. Acidic compounds, they tend to give food that kind of tart or sour taste. Vinegar, for example, contains ethanoic acid or acetic acid. So aqueous solutions of acids, they're called electrolytes, and electrolytes can conduct electricity. So acids cause certain chemical dyes called indicators to change colors, and that becomes very helpful because we have these things called pH indicators that kind of show whether or not a solution is turning acidic or basic. So there are some common acids. There's hydrochloric acid, nitric acid, sulfuric acid. The biggest thing that you kind of look on the side to take away from here is that they all contain hydrogen. And so that tends to be kind of a prevailing thought, that these hydrogen ions tend to be quite important when we start to talk about acid compounds. So bases, on the other hand, they taste bitter. Most bases are hazardous actually to taste. So because of that, we don't really consume a lot of bases. An example might be something like lime water, which is calcium hydroxide, but for the most part they're hazardous for our health. They also feel slippery, they change color of an acid-base indicator, and like acids, aqueous solutions of bases are electrolytes, so they conduct electricity. So, we've got a couple of different people we're going to go through. The first is our Arrhenius acids and bases. So we've got our Swedish chemist, Svante Arrhenius, came up with the idea that acids are hydrogen-containing compounds that ionize to yield hydrogen ions. So, in terms of the Arrhenius model of what he's kind of coming up with, he's saying acids are hydrogen-containing compounds that ionize to yield hydrogen ions. Now remember, ionization, all that means is that it breaks apart into its ions. So it starts out as a compound, separates out into its ions after that. So we tend to have this H plus and Cl minus that's here. He also added that bases are compounds that ionize to give us hydroxide ions. So in general, he's saying, okay, acids dissociate or ionize to give H+, bases dissociate or ionize to give us hydroxide, okay, or OH-. Acids are called either monoprotic, diprotic, or triprotic if they contain either 1, 2, or 3 ionizable hydrogens. So in this case, all you're doing is you're looking to see how many hydrogens are present, and in this case, H3PO4 is a triprotic acid. So there's some common bases after that kind of follow along. So we've got potassium hydroxide, sodium hydroxide, and you can kind of see the list, and taking from that in each one of them there is a hydroxide present, because hydroxide tends to be our indication for our Arrhenius base. The other thing with that is its solubility in water. So we can actually take a look at our periodic table, which I'd encourage you to do to kind of follow along with us for a second, and look at the metals compared to their solubility. So if we look at potassium and sodium, they are in group 1, our alkali metals, and so their solubility is quite high. Whereas if we start to get into group 2, calcium and magnesium, it starts to get a little bit lower in terms of their solubility. So they tend not to readily dissolve in water as much. So because of its corrosive nature, sodium hydroxide tends to be a major component of consumer products that gets used to clean, say, clogged drains and that kind of stuff. Sodium being soluble in water. And if you read the packaging for a lot of these cleaning products, they often tell you to pour this thing, the Drano in or cleaning product in, and then let it sit for so many minutes before flushing it with hot water. Because after the hot water hits it, it tends to be a little bit soluble, it dissolves in the water, and then ionizes and can pass through without causing any extra damage or anything like that. So the elements in group 1A, the alkali metals, they react with water to produce solutions that are basic. So we've got an example down below that has sodium plus water, and you can see that we have our sodium hydroxide that kind of comes from that, and a little bit of hydrogen gas that's made. So our group 1A metals, when they react with water, they tend to make these basic solutions. So from looking at the tables given for acids and bases, so basically if we go back and we take a look at our table for bases and our table for acids, there's a couple of questions that are here. I'd encourage you to pause the video, read through the questions, just try to come up with answers on your own, and come back when you're ready to go through them. Alright, so what elements do all of the acids in that acids table have in common? And we kind of touched on that. They all have hydrogen in common. Looking at the solubility of the bases, is lithium hydroxide likely to be soluble in water? Lithium turns out to be our group 1 alkali metal, and so our group 1 alkali metals that were there were also soluble in water, so we could say yes. We would expect lithium hydroxide to also be soluble in water. Hydroxides involved in group 2A elements increase in solubility as we move down the table. So they start at the top of group 2A, not really soluble, they have low solubility, and then they increase as they go down. So do you think beryllium hydroxide is soluble in water? We would say for that one, probably not. It would have a low solubility. And then what about something like strontium hydroxide, where strontium is a little bit lower down on the list below calcium, and then in that case it increases in solubility, so it would be more soluble as it moves down the list. So our next part, we have Bronsted-Lowry acids and bases. The Arrhenius definitions of acids and bases tend to be incomplete. So in 1923, we've got Johannes Bronsted and Thomas Lowry working separately proposed this new definition. And so this theory defines an acid. Okay, the Bronsted-Lowry theory defines an acid as a hydrogen ion donor, so it's something that's giving a hydrogen ion away, and a base is a hydrogen ion acceptor, so something that is taking in a hydrogen ion. So if we look at ammonia being dissolved in water, we have something that's kind of like this, where we have NH3 plus H2O, and then we get NH4 plus and OH minus. So we have this hydrogen ion acceptor in ammonia. It can take on an extra hydrogen. We have a potential donor in water, and then you can see that as this reaction happens, right, the ammonia takes on the extra hydrogen, and the water loses it and becomes our hydroxide. So because the reaction is in equilibrium, it can also go in reverse as well. So we could also have this hydroxide picking up the hydrogen and turning back into water, and the ammonia losing it and turning back into our ammonia compound. Or ammonium, so we turn back to ammonia. So let's make this just a little bit bigger to see. A conjugate acid is the particle formed when a base gains a hydrogen ion. So conjugate acid happens when a base gains a hydrogen ion. A conjugate base is just the opposite. It happens when an acid has donated a hydrogen ion. So those are just a couple of definition terms to kind of go through. But if we took a look at what we had so far with our formula, we can kind of see this pattern happening. Conjugate acids and bases are always paired with its base or acid respectively. So if I knew that NH3 was my base, because it's accepting a hydrogen ion, then my conjugate acid is NH4. It's the opposite that's there, right? It's the one that accepted that hydrogen ion. Whereas if I have my acid, my H2O, then I know that it lost a hydrogen, so its conjugate base is going to be that OH minus, that hydroxide. And so they're connected together. We have our acid and our base, and then it just gives us the conjugate acid and the conjugate base. Okay, just kind of saying that it either lost a hydrogen or picked up a hydrogen. So the Bronsted-Lowry theory also applies to acids as well. So in this case we have hydrochloric acid and water, and we know in this case that it's going to, the hydrochloric acid, the hydrogen part of it is going to be lost from this, and we're just going to have chlorine, or chlorine ion, chloride, and then we've got H2O, and that's actually going to become H3O, which we haven't seen very much before, but it picks up that extra charge. So we have our acid, we have our hydrogen ion donor. Okay, so these are connected. We have our base, which is our hydrogen ion acceptor, and then our hydrogen ion donor is going to end up leaving us with chloride, which is the conjugate base. Okay, because remember, the conjugate base is when an acid donates a hydrogen ion. The conjugate acid then is the one that picked up that hydrogen ion, and so it's our H3O that's here. So sometimes water accepts a hydrogen ion, other times it donates one. We've seen a couple of examples already with this. So water is amphoteric. It can act as both an acid and it can act as a base. So really, water then can't be determined to say whether things are acids or bases. We really have to look at the other compound to determine that. So our third part, Lewis acids and bases. So a third theory of acids and bases came from Gilbert Lewis. He proposed that an acid accepts a pair of electrons during a reaction, while a base tends to donate a pair of electrons. If you remember going through Vesper theory from before, they're also called Lewis dot structures. So Lewis was very big into how compounds form shapes, how molecular compounds can form shapes, and how electrons play the role in how they can combine together. So a Lewis acid is a substance that can accept a pair of electrons to form a covalent bond, whereas a Lewis base is a substance that can donate a pair of electrons to form a covalent bond. So acids, again in this case, accept electrons, bases donate electrons. So a hydrogen ion can accept a pair of electrons when it makes a bond, so therefore the hydrogen ion that we have here would be our Lewis acid. And then our ones that can donate that pair of electrons would end up being our Lewis base. And so in this case, when these combine together, we know this is going to form water, and so we have our H2O that's built out from there. So in this reaction, the hydroxide ion is also known as our Lewis base. So we have just an example to go through. So ammonia is widely used in fertilizers, plastics, and explosives. Identify the Lewis acid and the Lewis base in the following reaction involving ammonia. And so pause the video, take a look back, see if you can piece it together, and which you think is the Lewis acid and which is the Lewis base, and then come back when you're ready. Alright, so when we take a look at this, we notice that it makes just one product at the end. And so in terms of taking a look at the product side doesn't really help us. If we look at the reactant side, remember that we're taking a look for a Lewis acid and a Lewis base. Lewis acids accept a pair of electrons, Lewis bases donate a pair of electrons. So our Lewis acid, in this case, the one that is going to accept a pair of electrons is going to be our NH3. Okay, and it has this pair of electrons that's here, and it's going to be kind of sharing those with boron. Even though boron doesn't really need it, it will accept them to fill their octet that's there under different situations. And so we have our Lewis base being our, oh, sorry, I had those backwards. Sorry about that. Lewis base. Knew something didn't seem right there. A Lewis base because we have our electrons and it's donating them over to the boron, which would make our boron part our Lewis acid. Okay, so yeah, and that makes more sense now. So our Lewis base donating electrons over our Lewis acid, accepting those electrons to make that compound. So from there, there's a couple of questions for you to try. Let me know if you have any questions.